Picture this, a vast, uncharted expanse of space where invisible particles dance in the shadows, shaping the very fabric of reality. These hidden particles, though unseen, hold the keys to some of the universe's greatest mysteries. What if I told you that everything we know about the cosmos might only be scratching the surface? Hidden particles like dark matter and neutrinos are the silent architects of the universe, influencing everything from the tiniest atoms to the largest galaxies. Scientists believe these elusive particles could answer questions we haven't even thought to ask yet. In this video, we'll explore 30 fascinating theories about these hidden particles, theories that could change the way we understand space, time, and existence itself. Stay with us as we dive into the unknown, uncovering the secrets that lie just beyond our current knowledge. The journey begins now, and you won't want to miss a single moment. Now turning to the very foundation of our exploration, let's define what hidden particles are and why they captivate the scientific community. Hidden particles are theorized or observed entities that, as the name suggests, are not easily detectable using conventional methods. These particles play a crucial role in physics and cosmology, often filling in the gaps where our current understanding falls short. They are the missing pieces of the puzzle, influencing everything from the behavior of the smallest particles to the large-scale structure of the universe. What makes hidden particles so intriguing is their elusive nature. They rarely interact with ordinary matter, making them incredibly difficult to observe directly. For example, take dark matter, which makes up a significant portion of the universe's mass but remains invisible to us. Or consider neutrinos, tiny particles that pass through matter almost unaffected, barely leaving a trace. These examples highlight the mystery surrounding hidden particles and why scientists are so eager to uncover their secrets. By studying them, we not only deepen our understanding of the cosmos, but also challenge the boundaries of what we think is possible. Now shifting our focus, let's explore the standard model of particle physics, often hailed as one of humanity's greatest scientific achievements. This framework beautifully explains the fundamental particles that make up the universe: quarks, electrons, photons, and more, along with the forces that govern their interactions. Yet, despite its success, the standard model is incomplete. It doesn't account for gravity, leaving one of the universe's fundamental forces unexplained. More importantly, it fails to incorporate hidden particles like dark matter, which we know exists due to its gravitational effects but can't directly observe. The standard model also struggles to explain why neutrinos have mass or why the universe contains more matter than antimatter. These gaps have spurred scientists to look beyond the standard model, proposing new theories that could fill in the missing pieces. From supersymmetry to extra dimensions, these ideas aim to uncover what lies hidden in the fabric of reality. While the standard model has been incredibly reliable, its limitations remind us that there's still so much we don't know, and that's where the real excitement begins. Now turning to the intriguing theory of supersymmetry, often abbreviated as SUSY, we find a bold attempt to address the gaps left by the standard model. Supersymmetry suggests that every known particle in the universe has a hidden partner particle. For instance, electrons would have what's called a selectron, and quarks would pair with squarks. These partner particles are theorized to have properties that could explain some of the universe's greatest mysteries, particularly dark matter. One of the most compelling aspects of SUSY is that it predicts the existence of particles like neutrinos, which are stable, weakly interacting, and could make up dark matter. This would neatly solve the puzzle of why we observe the gravitational effects of dark matter but can't detect it directly. Additionally, supersymmetry could help explain why neutrinos have mass and why the universe has more matter than antimatter. Despite its elegance, SUSY remains unproven. Scientists have searched for these partner particles in particle accelerators like the Large Hadron Collider, but have yet to find conclusive evidence. This has led some to question whether supersymmetry exists at all, while others believe we simply haven't looked in the right energy ranges or with the right methods. For now, SUSY stands as one of the most promising yet elusive theories in the quest to uncover the universe's hidden particles. As we venture deeper into the mysteries of the universe, the concept of dark matter takes center stage. Dark matter, which makes up roughly 27% of the universe's total mass and energy, is invisible to us because it doesn't interact with light or other forms of electromagnetic radiation. Yet, its presence is undeniable, as its gravitational effects shape the structure of galaxies and influence the cosmos on the largest scales. One of the leading theories suggests that dark matter is composed of hidden particles known as weakly interacting massive particles, or WIMP. These particles are thought to be massive compared to other subatomic particles, but interact so weakly with ordinary matter that they've evaded detection so far. WIMP are particularly compelling because their properties align with what we observe about dark matter. They would move slowly, clumping together under gravity to form the invisible scaffolding of the universe. If WIMP exist, they could explain why galaxies rotate faster than predicted by visible matter alone, and why galaxy clusters behave as if they contain far more mass than we can see. Detecting WIMP directly is a monumental challenge, but scientists have devised ingenious methods to search for them. Experiments deep underground, shielded from cosmic rays, use ultra-sensitive detectors to look for rare interactions between WIMP and normal matter. Others aim to observe the particles indirectly by searching for the products of their annihilation, such as gamma rays in space. While no definitive evidence has been found yet, the hunt for WIMP continues to push the boundaries of technology and our understanding of the universe. Dark matter, whether composed of WIMP or other hidden particles, remains one of the most profound puzzles in modern science, and solving it could unlock secrets about the very fabric of reality. Now shifting our focus to another fascinating candidate in the search for dark matter, let's explore the mysterious world of Axions. These hypothetical particles were first proposed in the late 1970s to solve a puzzling issue in quantum chromodynamics known as the strong charge parity problem, or strong CP problem. This problem relates to the unexpected symmetry observed in the behavior of quarks and gluons, the building blocks of protons and neutrons. Axions were theorized to explain why this symmetry exists, and in doing so, they opened up a whole new avenue for understanding the universe. What makes Axions particularly intriguing is that they could also be a key component of dark matter. Unlike WIMP, Axions are extremely light and interact even more weakly with ordinary matter. This makes them incredibly difficult to detect, but it also aligns with some of the observed properties of dark matter. Researchers believe that Axions, if they exist, could be produced abundantly in the early universe and could now permeate space, forming a kind of cosmic sea that influences the motion of galaxies. Detecting Axions is no small feat, but scientists have devised creative experiments to hunt for them. One approach involves using strong magnetic fields to convert Axions into detectable photons. Another method looks for subtle changes in the behavior of light as it passes through magnetic fields in space. While definitive evidence of Axions remains elusive, the search continues to inspire innovative technologies and deepen our understanding of the cosmos. Whether Axions are the answer to the dark matter mystery or not, their study highlights the creativity and persistence of scientists in unraveling the universe's most profound secrets. Now shifting our gaze to another intriguing possibility in the realm of hidden particles, let's delve into the enigmatic world of sterile neutrinos. Unlike the three known types of neutrinos, electron, muon, and tau neutrinos, sterile neutrinos are a hypothesized fourth type that, as their name suggests, do not interact through the weak force, making them even more elusive than their counterparts. This lack of interaction with ordinary matter means they could pass through the universe virtually undetected, yet their existence could hold the key to some of the most pressing questions in physics. Sterile neutrinos are particularly fascinating because they could play a crucial role in neutrino oscillations, the phenomenon where neutrinos change from one type to another as they travel through space. Observations of these oscillations have hinted at the presence of a fourth neutrino, as the behavior of the three known types doesn't fully account for the observed patterns. Sterile neutrinos could fill this gap, providing a more complete picture of neutrino physics, but their potential significance doesn't stop there. Sterile neutrinos are also considered a strong candidate for dark matter. Their lack of interaction with ordinary matter aligns with the properties of dark matter, which doesn't emit, absorb, or reflect light. If sterile neutrinos exist, they could have been produced in the early universe in vast quantities and could now form a significant portion of the dark matter that shapes the cosmos. Detecting sterile neutrinos, however, is a monumental challenge. Since they don't interact via the weak force, traditional detection methods used for other neutrinos are ineffective. Instead, scientists rely on indirect evidence, such as anomalies in neutrino oscillation experiments or astrophysical observations. For instance, some researchers have suggested that sterile neutrinos could be responsible for certain unexplained features in the cosmic microwave background, or even the mysterious X-ray emissions observed in galaxy clusters. While the search for sterile neutrinos continues, their potential discovery could revolutionize our understanding of particle physics and cosmology. Whether they turn out to be the missing piece in the neutrino puzzle or a key component of dark matter, sterile neutrinos remind us of the boundless mysteries waiting to be uncovered in the universe. As always, the pursuit of these hidden particles drives innovation and inspires a deeper exploration of the cosmos. Now stepping into the realm of higher dimensions, let's consider the fascinating idea that hidden particles might exist in extra-spatial dimensions beyond the three we experience in our everyday lives. This concept, rooted in string theory, suggests that our universe could be far more complex than it appears, with hidden dimensions compactified or curled up at incredibly small scales. These extra dimensions could serve as a playground for particles that remain invisible to us, operating in spaces beyond our perception. String theory, one of the leading frameworks in theoretical physics, proposes that all particles are actually tiny, vibrating strings. These strings can oscillate in multiple dimensions, some familiar, like length, width, and height, and others that are compact or hidden from view. If extra dimensions exist, they could harbor particles that interact very weakly with our three-dimensional world, making them effectively hidden from our detection methods. This idea opens up the possibility that dark matter, for example, could consist of particles residing in these higher dimensions, only influencing our universe through gravity. The implications of extra dimensions for particle physics are profound. They could explain why gravity is so much weaker than the other fundamental forces, suggesting that its strength might be diluted across these additional dimensions. Experiments at particle accelerators like the Large Hadron Collider are searching for clues of extra dimensions by looking for energy signatures that could hint at particles escaping into these hidden realms. While no definitive evidence has been found yet, the search continues to push the boundaries of our understanding. This theory not only challenges our perception of the universe, but also invites us to rethink the nature of reality itself. If hidden particles exist in extra dimensions, they could be the key to unifying the forces of nature or solving some of the deepest mysteries in physics. The exploration of this idea reminds us that the universe is full of possibilities waiting to be uncovered, and each discovery brings us closer to a more complete picture of existence. Now shifting our focus to another intriguing possibility, let's explore the concept of Kaluza-Klein particles. These theoretical particles are thought to arise from the idea of extra dimensions, particularly in the framework of Kaluza-Klein theory, which unifies gravity and electromagnetism by extending our familiar three-dimensional space into higher dimensions. According to this theory, particles we know in our three-dimensional world could have counterparts in these extra dimensions, appearing to us as a series of particles with slightly different masses, collectively known as Kaluza-Klein particles. Imagine a guitar string vibrating at different frequencies to produce different notes. Similarly, particles in higher dimensions could vibrate in various modes, each corresponding to a unique particle in our observable universe. These higher dimensional vibrations would manifest as a spectrum of Kaluza-Klein particles, each with distinct properties. If these particles exist, they could provide direct evidence for extra dimensions, offering a groundbreaking insight into the structure of reality. One of the most exciting aspects of Kaluza-Klein particles is their potential connection to dark matter. Some theories suggest that the lightest of these particles could be stable and interact only weakly with ordinary matter, making them a perfect candidate for dark matter. If detected, they could solve two mysteries at once: the existence of extra dimensions and the nature of dark matter. Experiments like those conducted at the Large Hadron Collider are actively searching for signatures of these particles by looking for unusual energy patterns or missing momentum in particle collisions. The discovery of Kaluza-Klein particles would not only confirm the existence of extra dimensions, but also open up new avenues for understanding the fundamental forces of nature. It would bridge the gap between quantum mechanics and gravity, potentially leading to a unified theory of everything. As we continue to probe the mysteries of the universe, Kaluza-Klein particles remain a tantalizing possibility, reminding us that the answers to some of the deepest questions in physics might lie just beyond the dimensions we can currently perceive. Now turning to a theory that flips our understanding of the universe on its head, let's dive into the fascinating concept of mirror matter. This idea suggests the existence of a parallel universe composed of particles that are mirror images of the ones we know. These mirror particles would interact with our own universe only through gravity or perhaps other extremely weak forces, making them nearly invisible to our current detection methods. Imagine a world where everything we see, stars, planets, even atoms, has a hidden twin, identical in structure but operating under slightly different rules. Mirror matter could be all around us, yet completely undetectable by conventional means. This theory isn't just science fiction. It's a serious attempt to explain some of the most puzzling phenomena in the cosmos, particularly dark matter. If mirror particles exist, they could account for the missing mass in the universe, providing a natural explanation for the gravitational effects we observe without the need for entirely new particles. One of the most intriguing aspects of mirror matter is its potential to solve other mysteries as well. For instance, discrepancies in the behavior of certain particles, like neutrinos, could be explained by interactions with their mirror counterparts. Additionally, mirror matter could shed light on the asymmetry between matter and antimatter in the early universe, offering clues about why our universe is dominated by matter today. While mirror matter remains purely theoretical for now, scientists are exploring ways to test its existence. Experiments searching for deviations in gravitational forces or anomalies in particle behavior could provide indirect evidence. If proven, this theory would revolutionize our understanding of the cosmos, revealing a hidden layer of reality that has been right under our noses all along. As we continue to unravel the universe's deepest secrets, mirror matter stands as a compelling reminder that the answers we seek might lie in the reflections of what we already know. Now shifting our focus to another intriguing possibility, let's explore the idea of hidden sector particles. This concept suggests the existence of an entirely separate realm of particles that interact with our visible universe only through gravity or other extremely weak forces. These hidden particles could be a key piece in solving some of the greatest mysteries in cosmology, particularly dark matter and dark energy. Picture a hidden world operating alongside our own, filled with particles that are invisible to us because they don't interact with electromagnetic forces like light. This hidden sector could be teeming with particles that only make their presence known through their gravitational pull, which could explain why we see the effects of dark matter but can't detect it directly. What makes this theory so compelling is its potential to explain not just dark matter, but also dark energy, the mysterious force driving the accelerated expansion of the universe. Hidden sector particles could interact in ways that produce the repulsive effect we observe, offering a unified explanation for both phenomena. Scientists are actively searching for evidence of these hidden particles through experiments designed to detect faint gravitational anomalies or unusual particle interactions. If discovered, this hidden sector could open up a new frontier in physics, revealing a parallel universe of particles that has been invisible to us until now. As we continue to probe the cosmos, hidden sector particles remind us that there may be far more to the universe than meets the eye, and the answers we seek might lie in forces and particles we have yet to uncover. The exploration of this hidden realm could redefine our understanding of the universe and its most profound mysteries. Now venturing into the profound depths of quantum gravity, we uncover a theory that suggests hidden particles might hold the key to unifying two of physics' greatest frameworks, quantum mechanics and general relativity. At the heart of this idea lies the graviton, a hypothetical particle that could carry the force of gravity at the quantum level. Unlike the particles we're familiar with, gravitons would operate in the hidden corners of the universe, mediating gravity in a way that aligns with quantum principles. This theory is particularly intriguing because it addresses one of the most significant challenges in modern physics: reconciling the microscopic world of quantum mechanics, which governs particles, with the macroscopic world of general relativity, which describes the curvature of space-time. Gravitons could serve as a bridge between these two realms, offering a unified explanation for how gravity operates on both the smallest and largest scales. What makes gravitons unique is their potential to exist as massless spin-2 particles, a classification that aligns perfectly with the properties required to mediate gravity. If detected, they would not only confirm the existence of hidden particles, but also revolutionize our understanding of the universe by providing a quantum description of gravity. Scientists are exploring ways to detect gravitons through experiments that probe extreme gravitational environments, such as black hole mergers or the aftermath of the Big Bang. While these particles remain elusive, their discovery would mark a monumental leap forward in physics, shedding light on the hidden forces that shape our universe. As we delve deeper into the mysteries of quantum gravity, the search for gravitons reminds us that the universe's most profound secrets may lie in particles we have yet to observe. This exploration could ultimately reveal how the fabric of space-time itself is woven together, bringing us closer to a complete understanding of the cosmos. Now shifting our gaze to the cosmos' earliest moments, we encounter the fascinating idea that primordial black holes might be a unique form of hidden particle. These black holes are thought to have formed not from collapsing stars, as with the black holes we know today, but from the extreme densities of the universe's infancy, just fractions of a second after the Big Bang. Unlike their stellar counterparts, primordial black holes could range in size from as small as an atom to as massive as a planet, making them both invisible and elusive. One of the most intriguing possibilities is that these ancient black holes could account for dark matter, the mysterious substance that makes up a significant portion of the universe's mass. Because they do not emit light and interact only through gravity, primordial black holes fit the profile of dark matter candidates perfectly. If they exist in large numbers, they could be the hidden particles that have eluded detection for decades, silently shaping the structure of galaxies and the cosmos itself. Detecting primordial black holes, however, poses a unique challenge. Scientists have proposed several methods, including observing their gravitational effects on light from distant stars, a phenomenon known as microlensing. Another approach involves searching for the bursts of radiation emitted when these black holes evaporate, a process predicted by theoretical physicist Stephen Hawking. While no definitive evidence has been found yet, the search continues, driven by the tantalizing possibility that these enigmatic objects could unlock one of the universe's greatest mysteries. As we explore this theory, primordial black holes remind us that the answers to some of the most profound questions in physics might lie in the remnants of the universe's violent birth. Their discovery would not only confirm a new class of hidden particles, but also reshape our understanding of dark matter and the cosmos itself. Moving forward, the hunt for these ancient relics continues, offering hope for breakthroughs that could illuminate the universe's darkest corners. Now shifting our focus to another intriguing piece of the cosmic puzzle, we turn to the concept of magnetic monopoles. Unlike the familiar magnets we encounter in everyday life, which always have a north and a south pole, magnetic monopoles are hypothetical particles that possess just a single magnetic pole, either north or south. This idea, while simple in theory, challenges our fundamental understanding of magnetism and has profound implications for physics. Magnetic monopoles are not just a curiosity. They play a critical role in grand unified theories, which aim to combine the electromagnetic, weak and strong forces into a single framework. These theories predict that monopoles should have been produced in abundance during the high-energy conditions of the early universe. Their existence would help explain why electric charge is quantized, a phenomenon that has puzzled scientists for decades. Despite their theoretical importance, magnetic monopoles have yet to be discovered. This absence has led to what physicists call the monopole problem. If they were created in the early universe, where are they now? Some theories suggest they might be extremely rare or exist in regions of space we have yet to explore. Others propose that they could have been diluted during the rapid expansion of the cosmos, making them nearly impossible to detect. Efforts to find magnetic monopoles have included experiments with particle accelerators and searches in cosmic rays, but so far, no conclusive evidence has been found. Their discovery would be a monumental breakthrough, not only confirming a key prediction of grand unified theories, but also opening new doors to understanding the fundamental forces of nature. As we delve into the mystery of magnetic monopoles, we are reminded of how much remains hidden in the fabric of the universe. Their elusive nature keeps scientists searching, driven by the possibility that these single-poled particles could hold the key to unlocking deeper truths about the cosmos. And with that, we move closer to the next theory, where we explore the potential of hidden particles in cosmic rays. Now turning to the vast reaches of the cosmos, we explore the potential of hidden particles within cosmic rays. These high-energy particles, originating from events like supernova or black hole interactions, travel across the universe and occasionally collide with Earth's atmosphere. What makes cosmic rays particularly fascinating is that they might carry signatures of particles that lie beyond the standard model of particle physics. When cosmic rays interact with our atmosphere, they create cascades of secondary particles. Scientists meticulously study these interactions, searching for anomalies or unexpected behaviors that could hint at the presence of hidden particles. For instance, a cosmic ray collision might produce particles that don't fit into the known categories of matter, suggesting the existence of something entirely new. The energy levels in cosmic rays are incredibly high, far exceeding what we can achieve in particle accelerators like the Large Hadron Collider. This makes them a natural laboratory for probing the unknown. If hidden particles exist, they might only reveal themselves under such extreme conditions, providing a rare opportunity to glimpse physics beyond our current understanding. Experiments like the Pierre-Auger Observatory and the Cherenkov Telescope Array are at the forefront of this research. These facilities are designed to detect and analyze cosmic rays with unprecedented precision, offering a chance to uncover particles that could revolutionize our understanding of the universe. The search for hidden particles in cosmic rays is not just about finding new matter, it's about exploring the boundaries of our knowledge. Each collision holds the potential to reveal a piece of the cosmic puzzle, bringing us closer to answering some of the most profound questions about the nature of reality. As we continue this exploration, we move into the next theory, where we examine the WIMP miracle and its implications for dark matter. Now shifting our focus to one of the most compelling theories in particle physics, we delve into the WIMP miracle. This concept suggests that weakly interacting massive particles, or WIMP, could be the elusive dark matter that makes up about 85% of the universe's mass. The term miracle here isn't just for dramatic effect. It refers to the remarkable coincidence that the predicted properties of WIMP align almost perfectly with what we observe about dark matter. WIMP are theorized to be massive particles that interact only through gravity and the weak nuclear force, making them incredibly difficult to detect. Yet, their existence isn't just a wild guess. They naturally emerge from extensions of the standard model, such as supersymmetry, which we discussed earlier. This makes WIMP a particularly attractive candidate for dark matter, as they fit neatly into existing frameworks of particle physics without requiring entirely new laws of nature. One of the most intriguing aspects of the WIMP miracle is its ability to explain the universe's structure. If WIMP exist, they would have clumped together in the early universe, forming the gravitational scaffolding that allowed galaxies to form. This aligns with observations of how dark matter influences the cosmos, giving weight to the idea that WIMP could be the missing piece of the puzzle. Scientists have spent decades searching for WIMP using highly sensitive detectors buried deep underground, where they can avoid interference from cosmic rays. Experiments like the Large Underground Xenon experiment and the cryogenic dark matter search are designed to capture the rare interactions that might occur if a WIMP collides with an atomic nucleus. While no definitive detection has been made yet, the search continues with increasing precision, driven by the tantalizing possibility of uncovering one of the universe's greatest secrets. The WIMP miracle isn't just a theory, it's a beacon guiding us toward a deeper understanding of the cosmos. As we explore this idea further, we'll transition to the next theory, where we'll examine the concept of light-hidden particles and their potential role in solving some of the universe's most perplexing mysteries. Now shifting our focus to a fascinating alternative, let's explore the idea of light-hidden particles. Unlike the massive WIMP we just discussed, light-hidden particles are theorized to be much smaller in mass but still play a crucial role in the cosmos. One of the most talked about candidates in this category is action-like particles, which could hold the key to solving some of the universe's biggest mysteries. These particles are incredibly light, often billions of times less massive than electrons, and they interact very weakly with ordinary matter. Because of this, they've been challenging to detect, but their potential impact on our understanding of the universe is enormous. For instance, light-hidden particles could help explain why the universe is expanding at an accelerated rate, a phenomenon attributed to dark energy. They might also provide insights into the strong force problem in quantum chromodynamics, where the behavior of quarks and gluons doesn't quite add up without some missing piece. One of the most exciting aspects of light-hidden particles is their potential connection to dark matter. While WIMP dominate the conversation, action-like particles offer a compelling alternative. They could be produced in vast quantities in the early universe, eventually forming the invisible cosmic web that shapes galaxies and clusters. This makes them a dual-purpose solution, potentially explaining both dark matter and other cosmological puzzles. Detecting these particles, however, is no easy task. Their weak interactions with ordinary matter mean they don't leave behind the kind of tracks that heavier particles might. Scientists rely on innovative experiments, such as using strong magnetic fields to convert action-like particles into detectable photons. Projects like the Axion dark matter experiment are at the forefront of this search, pushing the boundaries of technology to uncover these elusive particles. The pursuit of light-hidden particles isn't just about finding a new piece of the universe's puzzle. It's about challenging our assumptions and expanding the horizons of particle physics. As we continue to explore these ideas, we'll transition to the next theory, where we'll examine how hidden particles might have played a role in the rapid expansion of the early universe. Now turning to the era of cosmic inflation, let's examine how hidden particles might have influenced one of the most dramatic events in the universe's history. Cosmic inflation refers to the rapid expansion of the early universe, a fraction of a second after the Big Bang, when space itself stretched exponentially. This theory explains why the universe appears so uniform on large scales, but it also raises questions about the mechanisms driving such an extraordinary event. Hidden particles could hold the key to understanding this cosmic expansion. Some theories suggest that these particles, which exist outside the standard model, might have acted as the fuel for inflation. For instance, certain types of hidden particles could have generated the energy density needed to power this rapid expansion. Their unique properties, such as weak interactions with ordinary matter, might have allowed them to dominate the early universe without leaving obvious traces in the cosmos today. One compelling idea is that hidden particles could have formed a kind of cosmic scaffolding during inflation, providing the structure needed for the universe to expand in such a smooth and uniform way. These particles might have also seeded the initial fluctuations in density that later gave rise to galaxies and galaxy clusters. In this way, hidden particles could be the invisible architects of the universe as we know it. Another intriguing possibility is that hidden particles might have interacted with the inflaton field, the hypothetical field responsible for driving inflation. This interaction could have influenced the rate and duration of inflation, shaping the universe's early evolution. By studying these potential connections, scientists hope to uncover clues about the nature of both hidden particles and the inflationary process itself. The search for evidence of hidden particles during inflation is ongoing. Researchers analyze subtle patterns in the cosmic microwave background, the afterglow of the Big Bang, to look for signatures of these elusive particles. If detected, such evidence could revolutionize our understanding of the universe's origins and the role of hidden particles in its earliest moments. As we continue to piece together this cosmic puzzle, we'll shift our focus to the next theory, where we'll explore how hidden particles might exist within the extreme environments of neutron stars. Now shifting our focus to the extreme environments of neutron stars, we explore how these cosmic marvels might harbor hidden particles. Neutron stars are the remnants of massive stars that have collapsed under their own gravity, creating some of the densest objects in the universe. A single teaspoon of neutron star material would weigh billions of tons, making them natural laboratories for studying matter under extreme conditions. The immense density and intense gravitational fields of neutron stars create an environment where hidden particles could thrive. Scientists theorize that these particles, which interact weakly with ordinary matter, might accumulate within neutron stars, altering their internal structure and behavior. For instance, hidden particles could affect the star's cooling rate, providing observable clues to their presence. One fascinating possibility is that hidden particles might form exotic states of matter within neutron stars, such as a Bose-Einstein condensate or a superfluid. These states could influence the star's magnetic fields or rotational properties, giving us indirect evidence of their existence. Additionally, hidden particles might interact with the neutrons themselves, leading to subtle changes in the star's stability or gravitational waves emitted during stellar collisions. Neutron stars also offer a unique opportunity to test theories beyond the standard model. By observing phenomena like pulsar glitches or the emission of X-rays and gamma rays, researchers can infer the presence of hidden particles. These observations could reveal how hidden particles behave under extreme pressure and density, shedding light on their properties and interactions. The study of hidden particles in neutron stars not only deepens our understanding of these cosmic objects, but also provides a window into the fundamental nature of the universe. As we continue to probe the mysteries of neutron stars, we may uncover clues that bridge the gap between known physics and the hidden particles that shape our cosmos. Next, we'll delve into how the Higgs boson might interact with hidden particles, opening new pathways to understanding the universe's hidden sector. Exploring new frontiers in particle physics, we now turn our attention to the Higgs boson and its potential interactions with hidden particles. The discovery of the Higgs boson in 2012 was a monumental achievement, confirming its role in giving mass to other particles. But could this particle also hold the key to uncovering the hidden sector of the universe? The Higgs boson is unique because it interacts with almost all known particles through the Higgs field. This interaction could extend to hidden particles, providing a rare opportunity to detect them. If hidden particles exist, they might couple with the Higgs boson in subtle ways, leaving behind faint signatures in particle collider experiments. For instance, unusual decays or energy imbalances in Higgs boson interactions could hint at the presence of these elusive particles. One intriguing possibility is that the Higgs boson could decay into hidden particles, which would then escape detection due to their weak interactions with ordinary matter. This could explain why certain measurements of the Higgs boson's properties don't always align with predictions. By studying these discrepancies, scientists hope to uncover evidence of hidden particles and their role in the universe. Additionally, the Higgs boson might act as a bridge between the visible and hidden sectors, offering a pathway to explore new physics. For example, hidden particles could influence the Higgs boson's behavior, altering its mass or decay patterns. Such interactions could provide critical insights into the nature of dark matter and other cosmic mysteries. The search for hidden particles through the Higgs boson is a major focus of experiments at the Large Hadron Collider. By analyzing vast amounts of collision data, researchers aim to detect the faint signals left by these particles. Success in this endeavor could revolutionize our understanding of the universe, revealing a hidden sector that has remained invisible until now. As we continue to probe the Higgs boson's secrets, we may uncover clues that connect it to the hidden particles shaping our cosmos. Next, we'll examine how the cosmic microwave background could hold traces of these elusive particles, offering another window into their existence. Now shifting our gaze to the earliest light in the universe, let's explore how the cosmic microwave background might hold secrets about hidden particles. The cosmic microwave background, or CMB, is the afterglow of the Big Bang, a faint radiation that fills the entire cosmos. It's like a snapshot of the universe when it was just 380,000 years old, offering a treasure trove of information about its origins. One of the most fascinating aspects of the CMB is its subtle variations in temperature and density. These tiny fluctuations, known as anisotropies, are the seeds from which galaxies and large-scale structures in the universe grew. But these variations might also carry hints of hidden particles. If such particles existed in the early universe, they could have influenced the CMB in ways that are still detectable today. For example, hidden particles might have altered the rate at which the universe expanded or affected the way matter clumped together in its infancy. These effects could leave imprints in the CMB's patterns, creating unique signatures that scientists can search for. By analyzing these patterns with incredible precision, researchers hope to uncover evidence of hidden particles that have otherwise remained invisible. Another intriguing possibility is that hidden particles could have interacted with photons, the particles of light. In the early universe, this interaction might have left a subtle distortion in the CMB's polarization, a property that describes the orientation of light waves. Detecting such distortions could provide a direct clue to the existence of these elusive particles. The study of the CMB is one of the most powerful tools we have for probing the mysteries of the universe's earliest moments. By meticulously mapping its variations and analyzing its properties, scientists are inching closer to uncovering the hidden particles that might have shaped the cosmos. As we continue to decode the CMB's secrets, we may find ourselves on the brink of a new understanding of the universe's hidden layers. Next, we'll delve into how hidden particles might play a role in solving one of the most perplexing puzzles in physics, the black hole information paradox. Now turning to one of the most baffling mysteries in physics, let's explore how hidden particles might hold the key to solving the black hole information paradox. At the heart of this paradox is a fundamental question: what happens to the information about matter that falls into a black hole? According to quantum mechanics, information cannot be destroyed, but black holes seem to defy this rule by consuming everything that crosses their event horizon, including information. Hidden particles could offer a groundbreaking solution to this puzzle. One possibility is that these particles act as carriers of information, preserving it even as matter disappears into the black hole. For instance, hidden particles might interact with the radiation emitted by black holes, known as Hawking radiation. As black holes evaporate over time, this radiation could encode the information of the swallowed matter, with hidden particles acting as the medium that ensures no information is lost. Another intriguing idea is that hidden particles could form a bridge between the quantum world and the event horizon of a black hole. They might create a subtle connection between the interior and exterior of the black hole, allowing information to escape without violating the laws of physics. This would mean that while the matter itself is lost to the black hole, its information is preserved in some form, perhaps encoded in the properties of these elusive particles. The implications of this theory are profound. If hidden particles can resolve the black hole information paradox, they would not only deepen our understanding of black holes, but also provide a crucial link between quantum mechanics and general relativity. This could pave the way for a unified theory of physics, one that explains both the smallest particles and the largest structures in the universe. As we continue to explore the cosmos and its hidden layers, the role of these particles in preserving information remains a tantalizing possibility. By unraveling their secrets, we might finally solve one of the most enduring puzzles in science and unlock a new chapter in our understanding of the universe. Next, we'll shift our focus to how particle accelerators are searching for hidden particles and what these experiments could reveal. Now shifting our attention to the cutting edge of experimental physics, let's dive into how particle accelerators are playing a pivotal role in the search for hidden particles. Among these, the Large Hadron Collider stands as one of the most powerful tools humanity has ever built to probe the mysteries of the universe. By smashing particles together at nearly the speed of light, the collider recreates conditions similar to those just after the Big Bang, offering a unique window into the hidden layers of reality. The hunt for hidden particles in particle accelerators is no simple task. These elusive particles, by their very nature, interact weakly with ordinary matter, making them incredibly difficult to detect. Scientists rely on the collisions within the accelerator to produce energy that could potentially manifest as hidden particles. The challenge lies in identifying their subtle signatures amid the chaos of high-energy interactions. Advanced detectors and sophisticated algorithms are used to sift through the vast amounts of data generated, searching for anomalies that could point to the existence of these mysterious particles. One of the key strategies involves looking for missing energy in collisions. If the energy before and after a collision doesn't match, it could indicate that hidden particles have been produced and carried away some of the energy. This approach has already led to exciting possibilities, such as the detection of particles that could be linked to dark matter or other hidden sector phenomena. Another method focuses on the decay products of collisions, searching for patterns that could reveal the presence of particles not accounted for by the standard model. The potential breakthroughs from these experiments are immense. Discovering hidden particles could not only confirm theories like supersymmetry or extra dimensions, but also provide new insights into the nature of dark matter and the unification of fundamental forces. Each collision at the Large Hadron Collider brings us closer to uncovering these secrets, pushing the boundaries of our understanding of the universe. As we continue to refine our techniques and analyze the data, the hope is that particle accelerators will reveal the fingerprints of hidden particles, opening up a new frontier in physics. Next, we'll explore how these particles might be connected to the phenomenon of quantum entanglement and what that could mean for our understanding of the universe. Now shifting our gaze to the quantum realm, let's delve into the fascinating relationship between hidden particles and quantum entanglement. This phenomenon, famously dubbed spooky action at a distance by Albert Einstein, describes how two particles can become so deeply connected that the state of one instantly influences the other, no matter how far apart they are. But what if hidden particles are the key to unlocking this mystery? Quantum entanglement has long puzzled scientists because it defies our classical understanding of space and time. If hidden particles exist, they might be the invisible threads weaving this intricate web of connection. Some theories suggest that hidden particles could act as mediators, carrying information or influence between entangled particles faster than the speed of light, bypassing the need for direct interaction. One intriguing possibility is that these particles belong to a hidden sector of the universe, interacting only through forces we don't yet fully understand. This could explain how entangled particles know each other's states instantaneously, as their connection might be facilitated by these elusive entities. Imagine hidden particles as unseen messengers, shuttling between entangled partners to maintain their cosmic link. Another angle is that hidden particles might emerge from the vacuum of space itself, a vast ocean of fluctuating energy that could give rise to temporary particles. These fleeting entities might serve as the bridge for entanglement, creating a dynamic network that underpins the quantum world. This idea ties hidden particles not only to entanglement but also to the very fabric of reality. Exploring this connection could revolutionize our understanding of quantum mechanics and hidden particles alike. It might reveal how quantum entanglement operates on a fundamental level and whether hidden particles play a role in this bizarre yet universal phenomenon. Could these particles be the missing piece that explains how entangled particles communicate across vast distances? As we continue to unravel the mysteries of the quantum world, the interplay between hidden particles and entanglement offers a thrilling avenue for discovery. Next, we'll explore how these particles might also hold the key to understanding the multiverse, opening the door to entirely new dimensions of reality. Now shifting our focus to the cosmos on an even grander scale, let's explore how hidden particles might hold the key to understanding the multiverse. The concept of a multiverse suggests that our universe is just one of many, each with its own unique set of physical laws and constants. But how do we even begin to explore such an idea? Hidden particles could be the bridge that connects these parallel universes, offering a glimpse into realms beyond our own. One theory proposes that hidden particles might exist in the spaces between universes, acting as messengers or conduits for interaction. These particles could carry information or energy across the boundaries of different universes, creating subtle connections that we're only beginning to detect. Imagine hidden particles as cosmic strings, vibrating across the fabric of the multiverse and linking distant realities in ways we can't yet fully comprehend. Another possibility is that hidden particles are the remnants of collisions or interactions between universes. In some multiverse theories, universes can collide or overlap, leaving behind traces of these encounters. Hidden particles might be the fingerprint of these cosmic events, providing evidence that our universe isn't alone. If we could detect these particles, it might confirm the existence of a multiverse and shed light on its structure. Hidden particles might also explain why the laws of physics in our universe are so finely tuned for life. In a multiverse, each universe could have different physical constants, and ours just happens to be the one where life is possible. Hidden particles could be the mechanism that transfers energy or information between universes, subtly influencing their development and creating the conditions we observe today. Exploring the connection between hidden particles and the multiverse could revolutionize our understanding of reality itself. It might reveal how universes interact or even how new ones are born. Could hidden particles be the key to unlocking the secrets of the multiverse, offering us a window into infinite possibilities? As we ponder these profound questions, hidden particles continue to captivate us with their potential to explain not just our universe, but the vast tapestry of realities that might exist beyond it. Next, we'll turn our attention to how these particles might also hold clues to the nature of time itself. Now turning to the intriguing relationship between hidden particles and the nature of time, we find ourselves facing one of the most profound mysteries in physics, the arrow of time. Why does time move forward and not backward? Hidden particles might hold the key to unraveling this enigma. Time symmetry, the idea that the laws of physics work the same whether time moves forward or backward, is a cornerstone of many theories. But our everyday experience shows time has a clear direction. Could hidden particles be the missing piece that explains this? One possibility is that hidden particles interact with time in ways we can't yet detect. These particles might carry information or energy that influences the flow of time, creating the one-way arrow we observe. Imagine hidden particles as tiny cosmic messengers, subtly nudging the universe toward a future state while leaving the past behind. This could explain why entropy or disorder always increases over time, a phenomenon that defines the arrow of time. Another theory suggests that hidden particles might be linked to the asymmetry of time on a quantum level. In the quantum world, particles behave in ways that sometimes seem to defy our understanding of time. Hidden particles could be responsible for these strange behaviors, acting as conduits that connect different moments in time. They might even allow for subtle interactions between past and future, hinting at a deeper, more complex structure of time itself. Hidden particles could also help explain why the early universe was so different from the universe we see today. In the moments after the Big Bang, time might have behaved differently, and hidden particles could have played a role in shaping its evolution. By studying these particles, we might uncover clues about how the arrow of time emerged and why it continues to define our reality. As we explore these ideas, hidden particles once again remind us of their potential to solve some of the deepest puzzles in physics. From the nature of time to the structure of the universe, these elusive particles could be the bridge that connects our understanding of the cosmos. With this in mind, we'll next delve into how hidden particles might arise from the fabric of the vacuum itself. Now shifting our focus to the fabric of the vacuum itself, we uncover another fascinating possibility: hidden particles emerging from what seems like empty space. At first glance, the vacuum appears to be nothingness, but in reality, it's a seething, dynamic realm filled with fluctuations. These fluctuations are tiny, temporary changes in energy that constantly occur, even in the most empty parts of the universe. Hidden particles might be born from these very fluctuations, giving us a new perspective on how the universe operates on the smallest scales. Vacuum fluctuations are a cornerstone of quantum mechanics, and they challenge our understanding of emptiness. Instead of being truly empty, the vacuum is a bubbling soup of virtual particles that pop in and out of existence. Hidden particles could be the next step in this process, emerging from these fluctuations in ways we're only beginning to understand. Imagine the vacuum as a cosmic nursery where hidden particles are continuously being created and destroyed, shaping the very fabric of space and time. These particles might also play a crucial role in cosmology. For instance, they could contribute to the mysterious dark energy that's driving the accelerated expansion of the universe. If hidden particles arise from vacuum fluctuations, they might carry energy that adds to the overall density of the cosmos, influencing its evolution on a grand scale. This could provide a missing link between quantum mechanics and cosmology, helping us understand how the smallest phenomena impact the largest structures in the universe. Moreover, hidden particles from the vacuum could shed light on the early moments of the Big Bang. In those initial fractions of a second, the universe was dominated by extreme energy fluctuations. Hidden particles emerging from this chaotic environment might have played a role in shaping the universe's initial conditions, setting the stage for everything that followed. By studying these particles, we could gain insights into the origins of the cosmos and the forces that drive its expansion. As we explore the connection between hidden particles and the vacuum, we're reminded once again of the universe's endless complexity and wonder. From the tiniest fluctuations in empty space to the vast expanse of the cosmos, hidden particles might be the key to unlocking some of the universe's deepest secrets. With this in mind, let's now turn our attention to how these particles could help solve one of physics' most puzzling questions, the hierarchy problem. Now turning to one of the most perplexing questions in physics, we examine how hidden particles could provide a solution to the hierarchy problem. This problem centers on the enormous disparity between the strength of the weak force and gravity. While the weak force is incredibly powerful on the atomic scale, gravity is astonishingly weak by comparison. This imbalance has puzzled scientists for decades as it challenges our understanding of how the fundamental forces of nature interact. Hidden particles could hold the key to unraveling this mystery. One possibility is that these particles act as mediators between the forces, introducing new interactions that balance their strengths. For example, certain hidden particles might influence how gravity operates on microscopic scales, bridging the gap between it and the weak force. This could explain why gravity appears so weak in our observable universe, despite being one of the four fundamental forces. Another intriguing idea is that hidden particles exist in higher dimensions as predicted by theories like string theory. In this scenario, gravity might leak into these extra dimensions, making it appear weaker in our three-dimensional world. Hidden particles could be the missing link that reveals how gravity behaves across these dimensions, offering a potential resolution to the hierarchy problem. This would not only address the imbalance but also provide a deeper understanding of the universe's structure. Moreover, if hidden particles interact with the Higgs boson, they could alter the way mass is distributed across different particles. This interaction might explain why particles like the W and Z bosons have such high masses compared to the gravitational force. By studying these interactions, scientists could uncover the mechanisms that govern the hierarchy of forces, shedding light on one of physics' most enduring puzzles. As we delve into the connection between hidden particles and the hierarchy problem, we're reminded of the intricate web of questions that still surround our understanding of the universe. These particles might not only solve the hierarchy problem, but also open the door to new discoveries about the fundamental nature of reality. With this in mind, let's explore how hidden particles could also explain another cosmic mystery, the tiny but non-zero mass of neutrinos. Now shifting our focus to another fascinating puzzle, we explore how hidden particles might hold the key to understanding the tiny but non-zero mass of neutrinos. Neutrinos, often called the ghost particles of the universe, are incredibly elusive, rarely interacting with matter. For decades, scientists believed they were massless, but experiments revealed that they do, in fact, have a tiny mass. This discovery raised new questions about how these particles fit into our understanding of physics. Hidden particles could provide a compelling explanation. One possibility is that neutrinos acquire their mass through interactions with these unseen particles. For instance, certain hidden particles might act as mediators, transferring small amounts of energy that give neutrinos their mass. This process, known as the seesaw mechanism, suggests that while neutrinos are incredibly light, there could be much heavier hidden counterparts balancing the equation. This theory not only explains neutrino mass but also hints at a deeper, more complex structure within the universe. Additionally, hidden particles might play a role in neutrino oscillations, the phenomenon where neutrinos change their type as they travel through space. These oscillations are only possible if neutrinos have mass, and hidden particles could be influencing this process. By studying these interactions, scientists could uncover new details about how neutrinos behave, shedding light on their role in cosmic evolution. The implications of this discovery extend far beyond neutrinos themselves. Understanding the source of neutrino mass could reshape our knowledge of particle physics and cosmology. For example, it might reveal connections between the neutrino sector and dark matter, another enigmatic component of the universe. Hidden particles could be the bridge that links these two mysteries, offering a unified explanation for some of the universe's most puzzling phenomena. As we unravel the connection between hidden particles and neutrino mass, we're reminded once again of the intricate tapestry of the cosmos. These particles might not only solve one of physics' lingering questions, but also open new doors to understanding the universe's fundamental nature. With this in mind, let's turn our attention to how hidden particles might even explain the Fermi paradox, the intriguing question of why we haven't yet encountered extraterrestrial life. Now shifting our gaze to one of the universe's most enduring mysteries, let's consider how hidden particles might hold the answer to the Fermi paradox, the puzzling question of why we haven't yet encountered extraterrestrial life. Given the vastness of the cosmos and the high probability of habitable planets, the absence of detectable alien civilizations has long baffled scientists. Could hidden particles be the missing piece of this cosmic puzzle? One intriguing possibility is that these particles influence the evolution of life in ways we're only beginning to understand. For example, hidden particles might play a role in the conditions necessary for life to arise and thrive. They could subtly affect the stability of planetary systems, the formation of complex molecules, or even the emergence of consciousness. If these particles interact weakly with ordinary matter, they might create barriers or pathways that shape the development of life across the universe. Another angle is that hidden particles could explain why advanced civilizations might remain undetectable. If extraterrestrial societies have harnessed or evolved alongside these particles, they could be using technologies or forms of communication that are completely alien to us. Hidden particles might enable phenomena like faster-than-light travel or cloaking mechanisms, making advanced civilizations invisible to our current methods of detection. Hidden particles could also influence the cosmic timeline of life. For instance, their interactions might accelerate or delay the development of intelligent species, creating a universe where civilizations rarely overlap in time. This would mean that even if life is abundant, the chances of two advanced societies coexisting and communicating are vanishingly small. As we ponder these ideas, it's clear that hidden particles might not just solve the Fermi paradox, but also deepen our understanding of life's place in the universe. By exploring their potential role, we're not only searching for answers about extraterrestrial life, but also uncovering the subtle forces that shape cosmic evolution. With this in mind, let's turn to the final frontier of hidden particle research, what the future holds for uncovering these elusive elements and the groundbreaking discoveries they might bring. Now turning to the horizon of scientific exploration, let's consider what the future holds for the study of hidden particles. This field is poised for transformative breakthroughs, with cutting-edge experiments and technologies designed to uncover the secrets of these elusive elements. One of the most anticipated projects is the next generation of particle accelerators, which will push the boundaries of energy and precision far beyond what we've achieved so far. These powerful machines could reveal particles that have remained hidden from our current detectors, opening new windows into the fabric of the universe. Another exciting frontier lies in the development of ultra-sensitive detectors capable of capturing the faintest signals from hidden particles. Innovations in cryogenic technology and quantum sensors are making it possible to detect interactions that were once thought to be undetectable. These advancements could finally provide evidence for particles like axions or sterile neutrinos, solving mysteries that have puzzled scientists for decades. Space-based observatories also play a crucial role in this quest. Missions designed to study the cosmic microwave background, gravitational waves, and high-energy cosmic rays could uncover indirect evidence of hidden particles. By analyzing subtle patterns and anomalies in these phenomena, researchers hope to piece together the role these particles play in the cosmos. Collaborations across disciplines are equally vital. Physicists, astronomers, and engineers are working together to design experiments that combine multiple approaches, creating a more comprehensive picture of hidden particles. For instance, combining data from particle accelerators with observations of distant galaxies could reveal connections between these particles and the large-scale structure of the universe. As we look ahead, the potential for groundbreaking discoveries is immense. Hidden particles could revolutionize our understanding of dark matter, dark energy, and the fundamental forces that shape reality. They might even provide answers to some of the most profound questions in science, such as the nature of gravity, the origin of the universe, and the possibility of extra dimensions. With these exciting possibilities on the horizon, the pursuit of hidden particles is not just a scientific endeavor but a journey into the unknown, one that promises to reshape our understanding of the cosmos and our place within it. Stay tuned, because the next chapter in this story could change everything we think we know about the universe. As we bring our journey through the 30 theories about hidden particles to a close, it's clear that these elusive elements hold the key to unlocking some of the universe's greatest mysteries. From the enigmatic nature of dark matter to the tantalizing possibilities of extra dimensions, each theory offers a unique perspective on the unseen forces shaping our cosmos. Together, they paint a picture of a universe far more complex and interconnected than we ever imagined. Hidden particles aren't just a scientific curiosity, they're a gateway to understanding the fundamental questions of existence. They challenge us to rethink our assumptions about reality, from the tiniest particles to the vast expanses of space. Whether it's through supersymmetry, actions, or sterile neutrinos, these theories push the boundaries of human knowledge, inspiring both awe and curiosity. As we stand on the brink of discovery, one thing is certain: the search for hidden particles is far from over. Each experiment, each observation, and each breakthrough brings us closer to answers that could redefine our place in the universe. So, what will the next discovery reveal? Will it confirm one of these theories, or will it uncover something entirely unexpected? The possibilities are as vast as the cosmos itself. Now we turn to you, the curious minds who dare to explore the unknown. What do you think lies beyond the limits of our current understanding? Which of these theories resonates with you the most, and what questions would you like to see scientists tackle next? Share your thoughts in the comments below, and don't forget to like, subscribe, and hit the notification bell to stay updated on our journey into the mysteries of the universe. Together, let's keep exploring, questioning, and discovering the secrets hidden within the fabric of reality.